I'd like to have you guys pull out your calculator and we're going to do a little bit of investigation first. And so if you could clear off your calculator, second plus 712, and under y2, I'd like you to, under y1, I'd like you to put in sine of x. Okay, now make sure that your mode is in radian, and if you cleared it, it's already in that mode. And let's set the window so it goes from a -5 to 5. And then also for the y, -5 to 5. All right, so our graph on this should be a basic sine graph, and it looks like this. Okay, so in our previous introduction video, I showed you that at 0, so right here, the linear approximation was y is equal to x. And so under y equals, if you could put in y is equal to x, and then let's fatten that graph up. So make that as a fat graph. So just press enter. And then I'm going to graph the two out. Okay, so from this, what we can see is that if you stick around x is equal to 0, this approximation of y is equal to x is fairly accurate, maybe from about here to here. But beyond that, right in this area, or maybe even in this area, it's not a very good approximation. Okay, so in order to improve on this approximation, I'm going to increase the power of the polynomial. So instead of having it as a linear approximation, I'm going to do another approximation and make it as a cubic. Right? So go back to the y equals. And then if you could unhighlight this, right? So I'm not going to get rid of it. I'm just going to not let it show up. And then go to the y3, and I'd like you to put in this function, this polynomial. X minus x raised to the third divided by 6. Okay, now you might be wondering how I got that random equation, but I'm trying to make it so that it's going to be a better approximation of the sine graph. Okay, so let's fatten this graph up. And then go to the graph. So here's my sine graph. And now here is my cubic approximation. Okay, so if you look at it, see how it's a little bit better? So before it used to just go straight through this way, but now it's kind of hugging the graph a little bit more closely. And so it's a better approximation. But still, if you go a little bit farther beyond to this region or to this region, it's not a good approximation. So let's go another polynomial over. And so I'm going to now ask you to turn off number 3. And now let's turn on, put in another equation for y4. And this time it'll be x minus x raised to the third divided by 6. And now I want you to add on plus x raised to the fifth and divide that by 120. Okay, so now let's graph this out. And here's our original sine graph. And now you can see that, oh, I think I forgot to fatten it up. All right, let me go back and fatten that up. So fatten this up slightly to this. And now let's look at it again. Okay, so you can see that now it's getting better and better, right? So if I went one more, then you can see that it's going to go up this way and over, but this is a pretty good approximation. All right, so if you were to do some discovery on this, you'll be able to see a pattern. There are two famous mathematicians who wanted to figure this out, and just by the title, you can probably guess who the mathematicians are. And the two mathematicians are Maclaurin and Taylor. All right, so let me give a first name to each one of them. So Maclaurin's first name is Colin, and he is a Scottish mathematician. And Taylor's first name is Brooke. and he is an English mathematician. Okay, so these two mathematicians are the ones who studied in depth about how to make a polynomial and make it as a representative for a more difficult function. Okay, so now if you could go to the class notes, and we'll just read through this. So a linear approximation is the same as a first degree polynomial approximation. The degree n of the polynomial corresponds to the highest derivative needed to create it. So if you remember, for the first degree polynomial, we needed to take the first derivative, and then that was your slope. The center was at x sub 0, so we started it off at 0, is also needed to create the polynomial. So the polynomial approximates the function well at x values close to the center. So if you remember, let me just go back to my calculator here. So my center is at 0 for this one. So anything that is in this particular area, it's going to be a good approximation. But if I change my center to somewhere way out here, this would not be a good approximation. These higher order polynomials are better approximations for a given function than the linear approximations. Okay, so if you noticed at going back to my calculator, y equals, look at the fourth graph that I put in, x minus x raised to the third power divided by 6 plus x raised to the fifth power divided by 120. These are not just random numbers, right? And so if x sub 0 is equal to 0, the polynomial is called a Maclaurin polynomial. Can you say that? Maclaurin polynomial. So this is where specifically it is centered at 0, right? So it's not going to be at any other point except for 0. And what he discovered is that, here is his theorem. It states that if f can be differentiated n times at 0, right? So this is where the center is. Then we define the nth Maclaurin polynomial for f to be the following, right? So this p is representing the polynomial. So polynomial of some degree, so nth degree, is equal to, you take the function f of 0 plus f prime of 0 of x. So if you recall, this right here, these two just together, this is the linear. This is the linear approximation. And then we're going to improve on the linear by taking another derivative. So it'll be f double prime of 0, and then you have to divide by 2 factorial, and then multiply it by x to the second power. And then you're going to keep adding another derivative, so it's plus f triple prime of 0 over 3 factorial times x to the third power. And then it's going to continue in this pattern. So the general pattern for a Maclaurin polynomial of the nth degree is f of, and then the derivative nth power derivative of 0 divided by n factorial, and then times x to the nth power, right? So this could go on for many, many terms. So if I asked you, what is the 10th order Maclaurin polynomial, you have to find f of the 10th polynomial of 0 divided by 10 factorial, and then it would be times x to the 10th power. And then of course, you have all the ones prior to that. Okay, so I would actually like to begin with not the first example, but the second example, because we've been looking at the sine graph. So if you could turn to page 3 in your class notes, and I want to go through and figure out how I got what I got from the calculator. All right, so go to the next page, please. Okay, so the question here is asking, find the nth Maclaurin polynomial for, and then we're going to look at the sine of x. So you first write out f of x is equal to sine of x, and then I want to find at 0, so it's f of 0 is equal to 1. Or I'm sorry, f of 0 is equal to 0. Then I take the derivative, so it's f prime of x is equal to cosine of x, and then f prime of 0 would equal 1 because the cosine of 0 is equal to 1. And then I continue with this. F double prime of x is equal to negative sine of x. So f double prime of 0 is equal to 0. And then f triple prime of x is equal to negative cosine of x. So f triple prime of 0 is equal to negative 1. All right, now I'm going to write out the Taylor polynomial on this. And so if you go back to, I'll just put up what my original one was on here. All right, so let's go back to this. I'll have both of these together. So by definition, I want to take the first f of 0. So then that would be f of 0. So that's going to be the same thing as the p sub 0 of x, and that is equal to 0. Okay, then to figure out what's p sub 1 of x, the polynomial of the first order, and so that would be the previous, so it'd be 0 plus x. And then I have the second order is going to be p sub 2 of x is equal to 0 plus x plus 0. So you can see that the first one and the 0 one and then the one that's the second one is going to cancel out, right? Because it's basically the same. And then you have p sub 3 of x is equal to, and then I'm going to be adding on a minus 1 over 3 factorial and then x to the third. Okay, and then p sub 4 is actually going to be the same as p sub 3 because I'm just adding on a 0. And then the fifth order on this is p sub 5 of x is equal to, here is our 0, here's our first order, second order, third order, fourth order, and the fifth order, right? So I'm just going to take away all of the zeros. And so you end up with p sub 2k plus 1. So notice that the first one is just going to be 0. So I'm just going to be starting with 1 on this. And so that'll be x. The second one gets skipped because you get a 0 here. So it's the same as this. And then the next new one is a minus 1 over x cubed over 3 factorial plus 1 over 5 factorial times x to the 5th power minus 1 over x to the 7th over 7 factorial, and so on. So this will keep on going. And then I'm going to write out my general term on this. So it'll be alternating in sign. So it's a negative 1 raised to the k power. And then it's 1 over, and it's 2k plus 1. So 2k plus 1 is just representing the fact that it's starting with 1, and then it's going to 3 and 5 and 7 and so on. And then you have x raised to the 2k plus 1. And this is where k is equal to 0, 1, and 2, and so on.